For years, NASA's Juno spacecraft has been our silent witness in the Jovian system, slipping past towering storms, weaving through Jupiter's intense radiation belts, and sending back snapshots of a world more alien and violent than we ever imagined. But now, as its mission nears its end, the data from its latest flybys has been decoded using advanced AI. And what it reveals is something scientists weren't prepared for. Beneath Jupiter's iconic cloud bands, inside its colossal storms, and even across the tortured surface of its volcanic moon, Io, the patterns tell a darker, more complex story than we thought possible. From a central cyclone at the pole that appears hollow to eruptions on Io releasing more energy than all of Earth's power plants combined, Juno's final gift to humanity may be a warning, one that could reshape what we believe about the most massive planet in our solar system. On April 18, 2024, Juno soared over Jupiter's northern pole, capturing an image that at first glance seemed familiar. 8 massive cyclones locked in a near-perfect ring encircling a brilliant central storm. Invisible in infrared light, it appeared to be a churning, powerful vortex. But when scientists compared the images across 3 different spectra, visible, infrared, and microwave, they stumbled onto something inexplicable. The microwave radiometer, capable of peering deep beneath the clouds, showed the surrounding cyclones radiating intense heat, their roots plunging tens of miles into Jupiter's atmosphere. The central storm, however, the brightest feature visually, was hollow. No heat, no depth, just a thin shell of cloud like a painted mask drifting above the chaos below. This empty heart challenges everything we know about storm dynamics on gas giants, suggesting the presence of a shallow, stable vortex powered by mechanisms we cannot yet explain. It's not just a meteorological puzzle. It could mean there are processes at work inside Jupiter that are unlike anything in our solar system. While Jupiter's storms defy expectations, its moon Io is rewriting the rule book on volcanic activity. Known as the most volcanically active body in the solar system, Io's surface is a hellscape of molten lakes, rivers of lava, and geysers that hurl plumes hundreds of miles into space. During a close pass, Juno's instruments recorded the largest eruption in Io's observed history, an inferno covering 25,000 square miles and releasing between 140 and 260 terawatts of energy, several times more than the total output of Earth's power plants. Using its infrared spectrometer, GRAM, and adapted microwave radiometer, Juno pinpointed exactly where Io burns the hottest, mapping a network of volcanic fields where magma still churns beneath a crust so thin and smooth it reflects like glass. AI analysis revealed how tidal forces from Jupiter and neighboring moons knead Io's interior like dough, creating constant frictional heat. This isn't just an active moon. It's a planetary pressure cooker. And Juno has shown us the lid might be rattling harder than ever before. For centuries, Jupiter's iconic bands of color were thought to be little more than atmospheric decoration, swirling weather patterns painted across its upper layers. But Juno's gravitational measurements have stripped away that illusion. The belts don't just skim the surface. They plunge 1,800 miles deep, a churning engine of jet streams more massive than 3 Earths combined. These atmospheric rivers race at over 220 miles per hour, spiraling in opposite directions. Light zones racing with Jupiter's rotation while darker belts fight against it. AI modeling of Juno's data suggests that these deep-flowing belts might be connected directly to the planet's internal heat engine, carrying energy from the metallic hydrogen layers up into the visible cloud tops. If true, it means Jupiter's atmosphere is not a separate skin over its body. It is its body, an integrated system where weather, chemistry, and internal structure are bound in ways we've never seen on another world. The Great Red Spot has raged for centuries, but Juno's high-resolution imaging and AI-assisted tracking have confirmed what astronomers feared. The storm is shrinking, shedding massive fragments of cloud hundreds of miles across that spiral away into the surrounding atmosphere. Once large enough to swallow 3 Earths, it can now barely fit one. Its shape shifting from an elongated oval to a near-perfect circle. And yet, paradoxically, the winds within it are accelerating, up 8% since 2009, creating a tighter, more violent vortex even as its footprint dwindles. The AI models suggest an unsettling possibility. If the storm collapses entirely, it could disrupt the stability of surrounding jet streams, triggering a cascade of atmospheric changes across the planet. Jupiter itself will survive, but the disappearance of this storm could be the first domino in a series of shifts that alter the planet's climate in unpredictable ways. Hidden deep within Jupiter's magnetic field lies a strange anomaly known as the Great Blue Spot, a concentrated region of intense magnetism near the planet's equator. For years, it remained relatively stable, shifting only slightly in longitude. But Juno's magnetometer readings from its latest passes revealed a startling change. The Great Blue Spot is moving eastward at an accelerated pace, stretching and breaking apart into smaller magnetic vortices. The AI analysis shows that these fragments are gaining strength even as the main spot weakens, a sign that Jupiter's magnetic field is reorganizing itself far faster than expected. On Earth, such rapid magnetic changes can precede pole reversals and trigger disruptions in our shielding against cosmic radiation. While Jupiter's scale and structure are vastly different, the idea that its magnetosphere could shift on human timescales raises questions about how its moons and their fragile atmospheres might be affected. From its polar orbit, Juno has had a unique vantage point to watch the massive cyclones at each of Jupiter's poles. At the South Pole, a central cyclone is surrounded by 5 others in a perfect pentagonal arrangement. At the north, the pattern is an octagon of storms encircling a central vortex. The AI's time-lapse analysis revealed something no one had noticed before. These formations subtly change their positions over time, but then return to near-perfect geometric arrangements, as if guided by an unseen organizing force. This kind of stable geometry in such a chaotic environment defies our understanding of atmospheric turbulence. On Earth, storms drift and dissipate with no regard for symmetry. But Jupiter's polar cyclones seem locked into patterns that resist disruption, suggesting there may be deep atmospheric waves or even magnetic interactions at play. During a series of close flybys, Juno's radio instruments picked up faint repeating bursts of emission coming from deep within Jupiter's atmosphere. At first, these signals were dismissed as background noise from charged particles spiraling in the planet's powerful magnetic field. But the AI's pattern recognition tools identified something extraordinary. They repeated every 10 hours, exactly matching Jupiter's rotation period, and were strongest when Juno passed over certain longitudes. This raises the possibility that these pulses are tied to a stable rotating structure deep within the planet, perhaps at the boundary between the metallic hydrogen layer and the molecular atmosphere. If so, these emissions could be Jupiter's equivalent of a seismic heartbeat, a regular signature of internal processes we've never observed on a gas giant before. While Io's volcanic fury is already legendary, Juno's AI-assisted data has revealed a disturbing new trend. The patterns of tidal heating across its surface are shifting, with some volcanic regions going dormant while entirely new hotspots flare to life. This suggests that the moon's interior is in a state of dynamic reconfiguration, possibly driven by subtle changes in Jupiter's gravitational pull as its own internal structure evolves. If this continues, Io could enter a period of hyperactivity with more frequent and more powerful eruptions than we've ever recorded. Such an increase could feed massive amounts of charged particles into Jupiter's magnetosphere, intensifying the planet's already lethal radiation belts. That in turn could make future missions to Jupiter's moons, even the ice-covered ones like Europa, far more hazardous than currently planned. Juno's mission began as an ambitious journey of discovery, a chance to unlock the secrets of the largest planet in our solar system. It was designed to map Jupiter's magnetic field, peer beneath its swirling cloud tops, and uncover the forces shaping its immense structure. For years, it sent back data that redefined our understanding of gas giants. But the latest AI-decoded datasets reveal something far more unsettling than scientific curiosity. They carry a message, a warning, that the Jovian system is not the stable, predictable world we once believed it to be. Consider the hollow heart of its massive polar storm, a vortex unlike anything in the solar system. The once prominent Great Blue Spot, a magnetic anomaly deep within Jupiter, is fading away as if erasing a cosmic signature. The planet's polar cyclones form perfect geometric patterns, maintaining a strange, and almost unnatural symmetry. Beneath the clouds, deep belts churn relentlessly, stretching thousands of miles into the planet's core, as if driven by forces we barely comprehend. Then there is the pulse, an electromagnetic rhythm emanating from within Jupiter, a signal that defies previous models. Coupled with the volcanic chaos of Io, which spews material into space like an uncontrolled geyser, these clues paint a startling picture. A system in flux, a magnetic engine operating on a scale akin to a small star, and it may be changing faster than we ever imagined. For a gas giant, evolution usually unfolds over centuries or millennia. But Juno's measurements suggest something extraordinary. These transformations are happening now, within a single human lifetime. We may be witnessing Jupiter caught in the midst of a rare, volatile transition, a planetary metamorphosis that could ripple across the solar system in ways we are only beginning to grasp. And Jupiter is no isolated world. It is a gravitational anchor, a cosmic shield, and a magnetic powerhouse that influences everything in its reach. Changes in its storms, magnetosphere, or volcanic moons could ripple across the entire Jovian system, altering radiation belts, shifting orbital dynamics, and possibly even affecting the flow of asteroids and comets through our own neighborhood. As Juno's time in Jupiter's deadly embrace comes to an end, it leaves us with an unsettling truth. The largest planet in our solar system is not a fixed backdrop to our cosmic story. It is an active, evolving force capable of changes that could one day matter far more to Earth than we want to believe. And perhaps, just perhaps, what we feared most is not that Jupiter is changing, but that it's only just begun.